binary search tree can be either a empty tree or a root node containing two children. One is left children and the other one is right children, by satisfying the following property. That is, the key value located at the root node should be greater than the key value located at the left child, and the key value located at the root node should be less than or equal to key value located at the right child. And the other form of the tree is it can have a root node like this, and this itself can be a left subtree. So this can be a left subtree and this can be a right subtree, which is in turn satisfying the properties of the binary search tree. Okay. We need to check whether this is a binary search tree or not. You can see this is left subtree and this is right subtree. Every node in the left subtree will be less than the root node key value. Yes, you can see all the nodes are lesser than the root node key value in the left subtree, and there is one node in the right subtree with a value called 10. It is greater than the root node key value 6. Now coming to this left subtree, inside this left subtree we have root node key value which is 3, and its left node key value 1 is lesser than the root node key value 3, and 5 is greater than the root node key value 3. Now coming to this subtree, the left node key value should be less than the root node key value. So it is satisfying the property, right? 4 less than 5. So every node is satisfying the property, hence it is said to be binary search tree. But if you consider the second binary search tree checking problem, okay, here this is not a binary search tree. Why? Because it has got a node called 11, and this key value 11 is greater than 6. So it should not be lying on the left subtree of this tree. Whenever a node key value is greater than the root node key value, then it should be lying on the right part of the subtree, right? So here it is lying on the left subtree part. Okay. And you can see there is a node with a key value 10 which is lying on the right side of the subtree, and this 11 is greater than 10, but it is lying on the part of left subtree. Okay, so this is clearly not a binary search tree. How we can search for an element in the binary search tree? For example, the element is 7. So we'll start our searching from the root node. This is the root node. 7 less than 20, condition becomes true. So searching starts in the left subtree. And now check this, 7 greater than 5, condition becomes true. So move to the right subtree. And 7 is compared with 15. Since 7 is less than 15, it must be occurring in the left subtree. Okay. So the left node is 9, 7 less than 9, condition true. You have to search in the left subtree part. And you can see this node 7 and whatever we are searching is also 7. Both are same. So finally we can say the element is found. Okay. And you can look at the steps here. Initially it will tell you to go left because 7 less than 20, go left. And then 7 is greater than 5, go right. And 7 is compared with 15. So again it will suggest you to go left. Next, 7 is compared with 9. 7 less than 9, condition true. So it will suggest you to go to left. And finally the element is found. Now this is the function which is used to search a key element in the binary search tree. So let us suppose we are considering a search function by passing root node and its corresponding key value. So let us suppose I want to search for an element called 4. Okay, so key value will become 4 now. And look at the condition immediately, root double equal to null. So initially root will be this node. Root double equal to null, condition false. Root dot key double equal to key, which means 4. Okay, 5 double equal to 4. Condition becomes false. So associated statement will not be executed. Then key less than root dot key. Key value is 4. 4 less than root dot key value, which is 5. 4 less than 5, condition true. Associated statement will be executed, which is again a recursive call. Search of root dot left comma key. So root dot left is node 3, isn't it? So 3, node 3, and key value is 4. That is what we are searching here. Now this will become the root node. In the second recursive call, this will become the root node. And if you see the execution of this recursive call, root double equal to null. Currently root is not null, so condition is false. Root dot key double equal to key. Key value here, root dot key value is 3. 3 double equal to 4. Condition becomes false. So associated statement will not be executed. Next, key less than root dot key. What is key value? 4. 4 less than root dot key 3. Condition becomes false. Then directly this return statement will be executed. Search of root dot right comma key, which means search function, recursive function search is called by passing root dot right. Root dot right is node 4. Got it? This is a node 4 and the key value is 4. In the next recursive call, root double equal to null. Condition becomes false. Root dot key double equal to key, which means 4 double equal to 4. Condition becomes true and it is going to return the root. It means the return type of the search function is node. So this particular node will be returned back to the calling function. Okay. So finally the element for which we are searching in the entire binary search tree is found, and it is going to return that node to the calling function. And how we can perform this insertion operation in the binary search tree? So let us suppose we want to insert an element called 1. 1 I want to insert. First it will check with the root node. Root will be representing this node initially, and 1 less than 5. So you have to perform insertion of node containing data as 1 on the left subtree of this binary search tree. Again, 1 is compared with this root node, that is 1 less than 3. Condition becomes true. Again go to left. Now 1 is compared with 2. 1 less than 2. Condition true. So here there are no other elements to the left of this node, hence the insertion happens at this position. Now let's create a binary search tree and understand how we can perform these operations. First node is 46. So there is only one node in this binary search tree right now, which is 46. Now 10 needs to be inserted. So the second step is 10 will be taken as the left child for this root node called 46, because 10 less than 46, so it must be placed as the child, left child to 46. Next, 23. Now 23 is compared with 46. 23 less than 46, condition true. and then it will go to left. 23 is compared with 10. So 23 is greater than 10. Condition becomes true. So 23 will be placed here. And the next node used for insertion is 90. First 90 will be compared with 46. 90 is greater than 46, so 90 should be inserted as the right child. And then node 12. 12 is compared with 46. 12 is less than 46, so insertion must take place in the left subtree. So it will move towards left. And again 12 is compared with 10. 12 less than 10, condition false. So 12 is greater than 10. So it will move towards right. So this condition is false. So it will move towards right. And then 12 is compared with 23. 12 is less than 23. Hence 12 will be inserted in this position. Next 54. 54 is compared with the root node 46. So 54 is greater than 46. So move towards right. And now 54 is compared with 90, and 54 is less than 90, condition true, and 54 is inserted as the left child. Okay. So this is the final binary search tree after performing insertion. Now let's understand insertion operation in binary search tree using Java program. First, we are considering a class called binary search tree. In order to construct a binary search tree, we need a node, isn't it? A binary search tree contains nodes. So, node will have totally 3 parts, isn't it? So, the first part will be left child. The second part will be key. And the third part will be right child. Node of item. You can see whenever I want to create a new node, then simply we are going to create a new node by passing its data. For example, node of 3. Okay. Then item value will become 3. So key is equal to item, which means key is equal to 3. So this is how it gets initialized. Left equal to right equal to null. Initially left equal to null and right equal to null. Okay. So like that we can create a node. And next, binary search tree will have a root node initially and it is null. Okay. We are initializing root node as null. For insertion operation, we are making use of insert function, which is calling insert record function. Okay. Insert REC function, which is taking 2 parameters. One is the root node of the tree. The other one is the key value which needs to be inserted. So after performing the insertion operation, the tree gets modified. The binary search tree is updated and that will become the new binary search tree. So root will be representing that newly updated binary search tree. So this is the purpose of writing root equal to insert REC of root comma key. So here comes the function which returns the node and takes 2 parameters, root node and key. First it will check root double equal to null. If the root is already null, then newly created node should be the root node. Okay. So whenever root is already null, it means we can say the binary search tree is empty. In that case, whatever node that you newly create, that will become the root node. So, and the root node will be returned. If suppose the key value is less than the root dot key, for example, you have created a root node like this. Now you want to insert a new node which is 1. Key value is 1. 1 is less than the root dot key value, which is 3. Condition becomes true. So it must be inserted as the left child of this root node. So this will become like this. Suppose we have another key value like 12, and this 12 is greater than the root node key value 3. Since this condition is true, it should be inserted as the right node to this root node, and finally this updated root will be returned. So initially root is null. Right now we have inserted a total of 3 nodes, and this is the newly obtained binary search tree, and when you return root you can access the entire binary search tree. Okay, so next this is for in-order traversal. Again, in-order function is calling in-order REC, okay, which takes a parameter as root, because we want to compute the in-order traversal for the binary search tree by passing root as the parameter. And whenever root is not null, then it is going to display the entire in-order traversal. We know the in-order traversal is first left node data will be displayed, and then root node data will be displayed, and then right node data will be displayed. Okay, so in this case data is nothing but key here for our example. So here for the class binary search tree we have created an object called tree and started calling a function like insert function by passing parameter as key value. So you can see the insert function that we have defined here. Insert function is taking only one parameter, that is key, and this key is also given as second parameter to insert REC function. Okay, so which means by considering the tree it is going to insert this value. Okay, initially tree will be null, so directly 50 will become the root node. Then insert tree dot insert of 30. So 30 is less than 50, hence it will be placed as the left child to this root node. And then 20 is less than 50, and again 20 is less than 30 as well, so it will be placed as the left child. And then 40, so 40 is compared with 50, 40 is less than 50, so it will move towards left, and 40 is greater than 30, so 40 will be placed as the right child to this node. And then 70 is compared with 50, 70 is greater than 50, so it will be placed as the right child to this binary search tree. And then 60 is compared with 50, 60 is greater than 50, and then 60 is compared with 70, 60 is less than 70, so 60 will be placed as the left child to this node. And then 80 is compared with the root node 50 key value, so 80 is greater than 50, so it will move towards right, and 80 is compared with 70, so 80 is still greater than 70, so 80 is placed here as a right child to node containing key value 70. And then we are calling in-order traversal function. So this is going to traverse the entire binary search tree in in-order traversal manner. So according to in-order traversal, first left node, then visiting node, then right node. So starting from this point, you can see left node is 20, and then visiting node is 30, and then right node is 40. So once the left subtree is completed, then it will consider the root node, that is visiting node is 50 right now, and then right subtree is considered. Within the right subtree, recursively again left node key value, visiting node key value, and right node key value will be displayed, that is 60, 70 and 80 in this order.